Hello, this lecture is about the workflow from a practical field application to a successful simulation. So we will discuss how you, from some kind of task that you might get when you're working in an engineering office or some other institution, to solve a problem using numerical simulations, and then what kind of information you need to get started and to conduct a then fruitful simulation. What kind of field application those could be were in hydrogeology in which you would consider numerical simulation useful. So you can conduct numerical simulations, for example, to simulate tracer tests. So you do tracer tests for a bunch of reasons in hydrogeology. But maybe you want to know, okay, assuming some kind of flow velocities, where it is best to install my observation watts, or where can I expect how far the tracer will travel, how maybe he will distribute in a heterogeneous subsurface. So that's where simulations can help you, for example, to plan the tracer test, or then when you got the results of the tracer test, you can try to simulate the same experiment and try to understand what kind of conditions caused you the observed results in the field. Also, for example, the plan of pump and treat applications is a good example for numerical simulation. So you have some kind of contaminant in the subsurface, you want to pump it out, you want to treat it on the surface and re-inject the clean water. And then you can, for example, optimal pump positions, pumping rates, that kind of setup you could simulate in a numerical model. Or also very classical is in groundwater management, how does the groundwater level change at different pumping rates? For example, you want to install a new groundwater well and you want to extract water from it. So you can see how far your domain will be influenced, the groundwater level will be influenced, how much it will decrease at different pumping rates. All those questions that might be difficult to answer analytically, but where numerical simulations are quick and helpful. And for example, also if you consider you want to have several groundwater wells, maybe at different depth, you can optimize well location to see that they don't influence each other. Or then there is some environmental issues and you want to protect some areas with having very little or no decrease in groundwater level. Then you can optimize this using numerical simulations. Or we want to know how the groundwater level changes at different discharge rates or at different recharge levels, right? So there are a bunch of applications very close to really real world problems that you can address with a numerical simulation. But how do you come from those kinds of topics to then a numerical simulation? This is what this lecture is about. So it's very important for the beginning for yourself to make clear what is the goal of the model, right? So when you're a modeler, people know that you're able to do modeling, then people will tell you about their interesting projects, about their interesting ideas, and they'll come to the question, well, can you model that? But then you have the question asking them back, why should I? Because people just think, yeah, well, it would be cool to have a model about that. But this is not a good cause to actually design a model. That's too much work for it, just to have it because, well, we can do it. What is the specific goal, the specific question you want to address using your model? And as more precise you are in defining your goal, as better you can design the model suitable for this specific goal. Because when you know your aim, you can subsequently derive the requirements you need to fulfill to have a successful model. Because once you know the aim and the situation, this defines your mathematical model. For example, do I only need to simulate groundwater flow? Or do I also have a transport process that I want to observe? Is my model transient or stationary? All this depends on my aim. Also, do I know the geometry of my problem, right? If I have a tracer test I want to simulate, one question, okay, how many days I am observing? Am I observing 10 days? Am I observing 100 days? Do I want to only know how the spread is, or do you want to have quantitative results? Do you want to have, for example, planning observation wells? Because how is the flow velocity? Is the high flow velocity high? I need to model a larger domain because the tracer is transported quicker over longer distances in the same amount of time. Right? So you see that is, once you define your goal and your project, there are subsequent questions you need to ask yourself, or you need to ask your client, to design a matching a suitable model. Right? And also with this comes, for example, parameters. So all those creators, people saying, well, can you model that? They don't have the necessary information, or the information you require are not well enough constrained to design a suitable model. When we're talking about groundwater modeling, we always need hydraulic conductivity and storativity. Right? These two basic parameters that we need every time. And if they say, well, yeah, it's some kind of sand, then, well, you can't work it, because the value range for hydraulic conductivity and for storativity for, well, it's sand, is so wide, the model the outcome could be anything. Right? So, for example, how heterogeneous is my material? Do I have a good database to design a suitable model? This is very critical, and a lot of models lack those. Right? That's really an issue. Also, the same is with boundary and initial conditions. Right? Do I have groundwater well somewhere? Do I have an idea about the aquifer thickness? Do I know if I'm confined or unconfined aquifer system? Do I have any idea about the pressure head in the region of interest? Right? So these are, subsequent questions you need to ask yourself, and then at some point you will notice, okay, it is possible to design a model, or you will come up to a point where you say, well, it's impossible to design a suitable model because I don't have the required information. So this is very critical, and it's also critical, and it's also your job as a modeler to say, well, I'm not able to conduct a suitable model because I don't have enough data. I don't know my parameters well enough. So this is a good guess, but nothing more. And it's also then your job, even if it's not your model, but you're reading a report of someone conducting a model, and you need to judge it, it's your part to say, well, how many data points did he actually use? Well, he's designing a 5 square kilometer region with one data point, one borehole where he conducted hydraulic conductivity tests. Right? You need to find the weak spots. And this very much comes with those kind of questions and this understanding of the system, what we try to train in this course. Here we go for a basic workflow. You have some kind of question, so it's beneficial if you start with some kind of question, as I said. So this is coming from the outside maybe. And from this question, the best is to design a concept. So we talked about conceptual models, and this is where they come in, right? So asking those basic questions I had before. What are the physical processes I'm looking at? Right, and then there comes the mathematical concept. Then from the mathematical concept, I maybe look for a suitable numerical framework. Then I'm looking, okay, what kind of parameters does this framework need? Some are going by transmissivity, some are going by hydraulic conductivity, right? So in principle, everything is convertible into one each another. But still, right, every model has its own demands. Geometry, all those kind of questions you have to ask. So you design the model, you set it up, you implemented it in the numerical framework you're using. Then you're conducting the simulation. And you're probably not just conducting it once, because then there is fine-tuning, spatial resolution, temporal resolution. You will notice, oh, my domain is too small. I need to run with a bigger domain because my flow velocity is higher than I expected. Whatever there is. So you do the simulation, it's a lot of work. And then there's also some kind of analysis of your results. I mean, it's not like, well, okay, I hit the run button, I got colorful pictures, and now I'm done. There's analysis, there's quality checking. Are my results feasible? Are they correct? Right? We talked about validation and verification. Can I validate my results? And then get the results themselves. Do they make sense? What is the consequence? You try to answer your question, right? So there once should be some question related content in your results and in your analysis. So you're probably writing some kind of report or so. So there's going back to the question, and well, any good simulation probably raises more questions than it gives answers. So you might want to do these all over again because there are then follow-up questions arising from the first analysis. But it's never a bad idea to start thinking about the analysis quite early on. Diving into this a bit more detail, I already mentioned is we started with the concept. So what kind of physical processes I need, what kind of parameters do I need, what I'm actually looking at. From there on, I'm deciding on my mathematical model. Right? This could, for example, if you want to model saltwater intrusion into a freshwater aquifer, density-driven flow is an important factor because the salinity water, so the seawater, will have a much higher density than the freshwater. So that density-driven flow effects. And not many usual groundwater flow models will incorporate it. The ones we are using in this course will not be able to tackle that kind of problems. So then, based on your mathematical model, once you know what kind of concepts are relevant, you will decide on your numerical model. Might be that you need to switch software. You can't use the standard software you've used all year long, because now there's a different problem. Always make sure that the code you're using is suitable for the application you're looking at. This is not standard procedure. Not everything is possible for everything. So make sure about that one. Then also a common mistake is people set up their model and say, well, okay, now I have all the parameters. Now I have everything ready. I just hit the run button and I'm done. That is not usually the case because simulation is an iterative process. You run your first simulation and you will come up with a bunch of errors. You might got instabilities and stuff we will have later in this course. So you're fine tuning, you're improving every time. At some point you might reach a result where you think, okay, this is something I can work on. But then you're thinking, okay, well, what was my question again? Oh, okay, so tracer concentration, I don't know, after 50 days. So how do I present that? So visualization is critical because you need to analyze your results, and to analyze your results, you need to visualize it. In numerical simulation, gives you usually so much of information. There are so many different informations you can get, right? So we're not just computing pressure head, but we're also getting flow velocities that both are spatially distributed. So it's at least 2D, maybe 3D domain. They might be changing over time. So there is so much information just for the flow, and then you might even have some transport processes. So you need to think, okay, what is the important information? And you need to extract that from this huge bunch of data. And this is done by visualization usually. So you can think, okay, do I want to show the 2D distribution, or do I want to have a time curve? So evolution of tracer concentration at my well over time. Things like this. And again, it's a good idea to think about this from early on. What kind of information do I actually want? And what are the steps I need to do to get this plot, this figure, something like this. So think about the visualization because it helps you aiming at the variables you actually want to see. And then you have analysis. Analysis of the quality of your simulation, right? So visualization also helps you, for example, to constrain your accuracy of your model, to constrain the stability of your model, all keywords we will have later on in this course. It also helps you then to analyze the question that was originally asked by the client at the very much of the beginning. So those three down here especially are kind of iterative process. So you run a simulation, you visualize the results, you analyze it, and then you might want to improve your simulation. And hopefully you don't have to go back very much to the top, but even this might happen, and it's good if you notice it because it means you're doing good work and you understand your problems and your weak spots. So I have very few best practices I want to give you at the head start. The first and most important thing is think, right? So the usual way students do is they start the software and they're just clicking around and trying to get things working and without any kind of concept, without any pre-arrangement. So really be careful. I always start a simulation with pen and paper, trying to make a sketch of the geometry, making clear, okay, what kind of boundary conditions do I have? And it's also reasonable when it's time, when you get experience, to think of, okay, what kind of result do I expect, right? I mean, if I have a very homogeneous region, I expect a very homogeneous pressure head distribution. And then if something strange pops up, something I didn't expect, this is where thinking, okay, is there a mistake or not? Why does it look the way it looks? But also be careful, because if the anticipated results are the results, you might think, oh, okay, everything is fine. But actually you have had a wrong thought from the beginning. So always be careful with that. But anyway, think before you start. Go careful, step by step. And that's also came with the next one, document what you did. So you can't conduct a simulation and just say you're in an office, conduct a simulation, you have a big presentation, and it's maybe 3 months before since you did the simulation, and then the client asks, yeah, what did you do there? And you have no clue, because you didn't document anything, you didn't write down anything. The good thing about numerical simulations are they are reproducible. They're field measurements that are not easily reproducible, because the amount of work is too much. But a simulation, a good simulation, is very well reproducible, but that means you need all required information. And documentation goes beyond just storing all the files you have been using, right? Do a consistent naming of files, meaningful names. Write down what you did between the different simulation runs, because as I said, we'll start with something and you will start modify this one and we'll start modify this one. So keep in mind what you change from time to time, what the effect was, so that you have, even after weeks of work, still remember what you did. I also strongly recommend to test early and often, right? So you do, a small change and you think, oh, well, okay, I just changed that. You can't break my simulation. And you do 10 other changes, and then you hit run and your simulation is just crap, or you get a bunch of errors and you think, well, why doesn't it work? And why isn't it working? Yeah, because at some point you probably did a mistake, and to find that one, do a change, test if everything is still working, still looking good. Okay, go on to the next change, right? Step by step, documenting it, think about what you do, test it. Also, I already recommended it before, visualization. What is the parameters, the variables you want to know in the end? Visualize them right from the beginning, so there's no surprises. And it's not like, working weeks or days on some kind of simulation and you notice, oh, that totally makes no sense. Well, if you should have looked at the results early on, right? So visualize it. To have an idea about the quality of your work right from the start. There are also some partly painful modeling experiences I want to share, because everyone does mistakes. This is normal, and some funny guys and researchers say, well, programming and simulation is 1% working and 99% finding your mistakes. And the most difficult mistakes are the trivial ones, right? It's a wrong minus sign somewhere. You forgot transferring the units. You load up the wrong files from a broken version. Whatever there is, it's usually trivial, but the trivial ones are the most difficult to find, right? So it's hardly to avoid all of them. You can avoid a lot of those if you work carefully, if you work slow, if you work step by step. It's more easy to find them if you documented it, all right? But this is part of the modeling experience, right? So having some frustration from time to time is okay, but there is a way out. It just takes time sometimes, and it also is helpful if you explain your problem to others, if have a new pair of eyes looking at it, because then you're more open to those trivial things, because then it's a question like, why did you do that? And you're like, oh damn, no, I shouldn't do that. And then you fall on your back. Okay, so this is part of the experience, just to prepare you. The other one is if you anticipated results look good, it still doesn't mean they are correct, right? So you always should validate your results, making sure that things are correct. Don't rely on your feeling, don't rely on your suggestion. So always be there on the safe side. Don't get a false positive. Right? Also, the other one is more trivial. Is if it looks wrong, there probably is a mistake, right? Don't show a simulation where you have the impression, oh, that yeah, there is something wrong, but I don't know where. So no. If it looks wrong, fix it. If it's wrong, fix it. Right. That's why visualization is so important. And also, as you said before, is some getting the false impression that, well, now I had my concept and run my simulation, I put in all the parameters, I only have to click the run button and everything will be fine. No, this is just the first step. Now the other half of the work, or even more of the work, starts. So be realistic in your time estimations. So, and this is also an experience which is not painful, which is there after all this negativity to keep you up your mood. There are correct, meaningful models, all right, and they exist. It's possible to achieve that. It's maybe not so easy at the beginning, or well, it might be, hopefully is easy at the beginning, but once complexity arises, it's getting more difficult. But there is a way out, and it's just really experience, training to get used to all those kind of workflow also, which is probably kind of new for most of you. I want to show now all the theoretical parts I discussed so far on a practical example. So I thought of here pump and treat scenario. So we have some kind of toxination in the groundwater. It can be some old industrial plant or whatever. I don't care. Some kind of contaminant infiltrated in the subsurface, contaminated the groundwater. And now you're working in an engineering office and your boss says to you, well, tell me where you would install the pump and treat setup. And well, because you're so enthusiastic, you decide to set up a numerical model for that. So for those of you not strictly familiar with what a pump and treat scenario is, so here in black I try to draw the contamination on the site. So here's my old industrial plant, whatever they had as a toxic substance, it is infiltrating into the groundwater. And so the idea is at some point you install a well where you pump up the water, all the contamination hopefully, and you do some purification. So you clean the water on the surface and you re-inject the extracted water back to the aquifer system in some way downstream. So you see there come a couple of critical parameters. Where's the best to install that kind of extraction well? You want to re-inject the water not too close to it because you don't want to have those two wells influencing each other. But also as further away you go, you have to transport the water, the costs are rising. So there is some optimization you can do. I don't want to go too much in detail into these pump and treat testments, but just to give you an overview about what can be done and why numerical simulations are helpful in such kind of scenario. So I draw here a little map. It's a well-observed site. So here we have our old factory, and there is a supposed origin for the contamination. We got some groundwater levels here, and we even have some kind of observation wells which you use to derive these groundwater levels, which was used to detect the contamination. So this is kind of your domain. And this is already quite a good database, right? Because we get groundwater levels, so we can define boundary conditions. It seems like the domain is very homogeneous. There is no banding of the groundwater lines, but still there are no observation wells in between, so we don't know. Maybe there's something we just simply haven't detected yet. right? But there are observation wells, so we might, could validate our model with the measurements of those wells, whatever there is. So that's already quite a good background. Now, how do you go? What is your concept? What are the questions that should be now running in your head? So the aim is pretty clear. We want to have pump and treat setup. What do I need for that? I need groundwater flow modeling because I want to know the flow velocity, which I need for my transport modeling. Right, so I have a diffusive, dispersive, advective transport because I have an active aquifer which is flowing from left to right or from east to west. So to describe the contaminant distribution in the subsurface, I need the groundwater flow modeled with the transport modeling. This also means I have a transient model, right? Not necessarily for the flow. We don't know if the flow is changing a lot, depends on variation in groundwater levels, depends on what kind of contaminant is it. Does the contaminant influences, for example, my density or such kind of stuff? Then it would also, the flow modeling would be transient. But we could, in this scenario, I could assume, okay, in the most simple case, the flow velocity is static. There's no much in variation in groundwater levels. So I have a transient model only in terms of the transport. But then the question is, okay, what kind of spatial resolution do I need, right? So for planning this pump and treat requirement, what is my aim with what kind of accuracy I want to model the spread of the contaminant, how accurate I need to provide the precisions for the wells, for the pump and treat setup. All those kind of questions that are involved in that. And then also you'll learn later in this course, accuracy and stability also depend on my spatial resolution. So questions I need to ask myself. But I also need to know a bit more background. I didn't go into detail in describing the scenario, but like, is a contaminant dissolved? That would be a huge different kind of physical process if I have precipitation maybe of the contaminant, or if the contaminant influences flow behavior, or if the dissolved contaminant has a higher density, so it's sinking towards the bottom of my aquifer, right? I kind of indicated that on my sketch above. So there are a couple of questions that need to be asked and that constrain then my mathematical model. But then again, we already talked about, for example, spatial resolution up here. We were talking then about the geometry when setting up the model. How large does it have to be? Depends on the flow velocity as well, right? So, and the time frames I'm looking at. Do I have enough data for my boundary conditions? So in the sketch I showed above, there was pretty good database, but sometimes it's suitable to extend, for example, my model domain, because then I have good information on the boundaries due to some wells or whatever, right? So there is here a couple of questions to ask yourself, and this is continuing, because then once you decided on your numerical model, you want to know, okay, what kind of parameters do I need? So as I already said, we need flow and transport, so we need at least transmissivity and storativity. We need all these diffusion dispersion coefficients. Then again, what kind of contaminant is it? Is there maybe some retardation effect? Is it decaying? Is it a biological contaminant, or are there chemical reactions going on? Do I have data for all this? So you see where the complexity arises when setting up such kind of models, right? So there really is required information to setting up the model, and you may or may not have those kind of informations. So then you're back to literature values, having best guess, things like this, which is fine in some parts, but of course are weak spots, right? And again, these are all these questions are, if someone presents you a numerical simulation, this is all the questions you should ask the modeler if he's not answering it in his report. How do you parameterize your model? It's a valid question, and you will get a lot of modelers sweating with that kind of questions, because usually the data we have for parameterization is very little, right? And this is always is a question totally valid to ask. And the same is for the initial and boundary conditions, right? So here I had my groundwater model, but as I said, there were no wells in the middle. So assuming homogeneous subsurface is just my best guess on the data I have. But, well, maybe my results will show I can't explain the experimental findings in the field with a homogeneous model. So maybe I want to do some geophysics or some in-depth, more drilling, more in-depth analysis of the subsurface to see if there are some underground structures which are inhibiting flow or changing hydraulic parameters of my aquifer in some way, right? And for example, here when I have a chemical contaminant transport, I was thinking, okay, what is my background concentration? Or can I separate enough my contaminant from what I have as a background? And those questions I'm asking here is just what came to my mind when I was designing the lecture, but there is no claim on completeness. Right. So there's, depending on the setup, there are way more questions to ask yourself, and it's good to be aware of those questions and try to answer as much of those at the beginning. You will note usually that while you set up your model, you will note, oh damn, I need that information as well. But that's okay. Things happen. You can't think about everything from the beginning, but trying to cover as much as possible is good. It's also like, you said, you have an office or something and the client wants you to set up this model. You will say, well, okay, but then I need this and this and this and this and this. And then you will usually get a strange face and say, well, oh, I don't have all that kind of information. And then, well, then you need to find a solution and you need to find somehow to constrain your input to your model. All right. But so having this and this comes with experience, getting to know what are important informations you need. So then, setting up your model, you hit the run button, you're happy, you get colorful pictures, but now the validation. Right? And in the scenario I had, this is quite good because we had so many wells, so we can compare groundwater levels to the wells. We can maybe have already an estimation about the flow velocity. Or you can do this with pen and paper because it's homogeneous subsurface. So you can calculate what you would expect as a mean flow velocity. You probably, because the whole issue came up, so they probably observed some high concentrations of the contaminant in their water samples. So you can compare the measured concentrations in the wells or in the observation points with the calculated contamination. You can maybe compare the spatial spread of the contaminant, which kind of wells are affected, which are not. And then you will probably find in some spots some disagreements, and then you can think of, okay, why? What do I do different in the model than from what might be actually the case in the field application? So there can be mistakes in the model, but sometimes you will always find, okay, the way the measurement was taken is different to what I'm calculating in the model. So sometimes you can live with some kind of disagreement between model and observation if you find a good reason for it, right? But because also sampling methods, also determination of some kind of parameters in the field are not directly comparable to what you're using in the model, right? So this is good to keep in mind that it's not always just a fault of the model, but also just simply methodological differences. Yeah, this is good to think about. And usually the boundary conditions have a huge effect. Yeah, so people are estimating how much changing the boundary conditions will actually have effect on their input model. Just a little bit change in hydraulic gradient will cause you different flow velocities and might change even flow direction, things like this. And of course, you always have to ask, okay, do I cover in my model all relevant processes? As I said, if I have a contaminant that is more dense than the water and it's sinking towards the bottom of my aquifer, maybe, for example, then my observation wells aren't deep enough to cover all this, and the contamination is actually much higher than estimated. Do I build something like this in my model or not? Questions to ask, to trust, which is situation specific. I can't give you a general comment about that one here. It always depends on the specific scenario you're looking at. But giving here you an idea about what to think about when you're talking about the validation of a model. And then the coming problems. So even you validated maybe your model correctly, but you just notice, okay, the assumption of a homogeneous subsurface doesn't hold, doesn't explain my concentration. Could be something like this, right? Or well, the hydraulic conductivity that was estimated, I don't know, for pumping tests or maybe through laboratory tests, doesn't explain what I see in the field. Also, you know, especially for those kind of contamination from old plants, the location of the contamination site is wrongly reported. Yeah, typical issue. Or you made your domain too large, too small, the spatial resolution is not fine enough, or the temporal resolution is too coarse. So many issues which you can fix. But you know, going back, thinking about where do I need to start changing, what are the other effects, side effects of those changes. Some of those, especially here regarded to domain, spatial and temporal resolution, we will have in subsequent lectures. But yeah, this is part of the process. Just get used to it. There's nothing wrong with that. It's just part of it, and you will get better every time. You might have noticed before during my lectures, and especially during this one, modeling has a kind of specific kind of humor, and so I want to share those three links with you, which are two of those are specifically to sciences. It's just to show you you're not alone. Yeah, many people feel the way about modeling, especially when they start modeling the way you do. But you learn from most of these why it's satiric and humoristic. There's always a truth to it. So you can read about it just for fun, and yeah, get to know that you're not alone, and it's just part of the process, and you will learn something about it. Also, kind of best practices, experiences, and stuff like this. The last one is a bit more philosophically. It's also yeah, kind of humoristic, but there is more truth to this one than to the other two links. There was a statement from a famous mathematician, statistic person saying all models are wrong, and then it was later extended to but some are useful. And this goes to what is said on the very beginning of this lecture series, is all models by definition are approximations, and as an approximation you can take the standpoint and they are wrong. But it's a Wikipedia article. You can read through it. It's yeah, you might learn about something. It's a bit philosophic. Also has some fun to it. So I recommend just reading it and enjoy. Take the information from it as personal experience. So what I wanted you to know from this lesson and to learn from this lesson is getting to know how you can start. When you get that kind of modeling task, that you're not lost in the field, but you know, okay, now I have to think about this one. Now I have to think about this one. Sharing with you a bit of the experience in terms of, you know, what to do, write down, start with pen and paper, draw a sketch, what kind of expect, what kind of parameters, you know, questions to think of. And it is that there is no complaint about completeness. It's just an inspiration for you what you can everything consider, and depending on the situation there are more or less questions to ask, and we will try to start easy and simple, but this one is considered a starting point. Thank you very much.